Hello everyone. In this video we are going to talk about the MATLAB Camera Calibration App. Now when you go to MATLAB there is more than one camera calibration app, but this is for single camera because there is also a stereo camera calibration and there is a basically LiDAR based camera calibration. So this is the simple one. And since in the previous video we talked about the notion of camera calibration, right? Estimating the intrinsic and extrinsic camera parameters from pairs of real-world coordinates of the points and their pixel coordinates, right? We learned all about how to calculate them mathematically. Now in this video we're going to show you how to do it in MATLAB. So if you go to MATLAB, and instead of the home tab that you normally add, you click on the apps tab. Here, if you expand the apps, you see all different types of apps for different applications. And under the image processing, you go down here and computer vision, you see these are different apps that MATLAB has. Some of them we'll try to use later, okay, like image segmentation app, right, region analysis app, the registration estimation, if we can, we talk about that and so on, right? There are some very nice ones, but as I told you, you see there is camera calibration, LiDAR camera, and then a stereo, and this is the one that we need. You click on this camera calibration app and then you get this window. Here you have two ways to add your images for calibration, and the images that you should be taking are from a chessboard. So what you need is a chessboard, and the important thing that it says is the chessboard has to be asymmetric. It doesn't say right in the beginning, but when you move forward it says so, that the chessboard better be asymmetric, which means instead of being 8 by 8 you make it like 8 by 7 or 8 by 6 or something. And why is that? So it can keep locating the same point as the origin of the chessboard in all of the images. Because if it's 8 by 8 due to symmetry, in one image it can, for example, detect the top left corner of the chessboard as the origin, while in the next image it can detect the top right corner as the origin. And so it causes a bunch of unwanted rotations and ruins the result of your camera calibration. Even if you go to Google and search for a chessboard, right? So you just check, search chessboard and get a chessboard like this or this, any of them, and you print it. Make sure before you print it, you remove one row of the cells, right? Just open it in Paint and crop it. So make it like 7 by 8 or something, and then print it. Once you print that chessboard, then now you can use your webcam, either the laptop webcam or camera or computer webcam, a separate USB webcam or something. Use that to capture the images. If the images are already captured and saved, then you can just click here and browse it. So when you click here, if you say from file, you have to browse existing images. Otherwise, when you click here, it is going to allow you to use your USB webcam. And if you don't have a USB webcam that is already basically added to MATLAB, then you have to add the hardware support package for it. When you go to MATLAB help and you click here, once you go down below, it shows all of this hardware support packages that you have installed. And if you need to use a USB webcam, you have to install this MATLAB support package for USB webcams. Okay? If you don't have this, your USB webcam, even if you connect it to USB port, is not going to work. So go to Adds On, go to Get Hardware Support Packages, search for USB webcams, and then if you have a MathWork username and password, you should be allowed to, here, it's this guy, to install it. Once you install it, then MATLAB easily recognizes your USB webcam and allows you to capture all of the pictures you need. The important thing when you take those pictures is You put the camera for each one of the 20 pictures. You need minimum of 20 pictures for a good calibration. Try to move the camera with respect to the chessboard. So this is the chessboard. I took a picture of it, and as you can see, I cropped it. Now it is 7 vertical and 8 horizontal, so I made it asymmetric. And these are these different positions and orientations of the webcam compared to or with respect to the chessboard, this black piece here. When I took those pictures, as you see, I moved them around, I moved them closer, further away, and rotated in different orientations and took pictures at different orientations and positions. Okay, you should not keep taking pictures at the same location and orientation all the time. Otherwise, those pictures all look the same and they are not any useful. The important thing is make sure those pictures really only contain your chessboard pattern and not a lot of background. Otherwise, then later you have to crop them and process them, and MATLAB is going to have a hard time basically using those. So let me show you what I mean. So here I have printed that chessboard pattern, and I'm going to use my webcam and show you how you can capture these pictures. And then, but ultimately I use all of those pictures that I have already saved, which are here. You see I have about like 40 images or so that they're all good, and you clearly can see different orientations and positions for them. And this is that pattern I have printed. So here, if I go and say add images, but I say from camera, right now it is going to try to use the USB webcam here. You see, this is the USB webcam now that I have, correct? You see here, it's connected. And now, as I said, I'll try to make sure that the only part that is in the image is the chessboard, okay? But I keep rotating, I keep moving it in all sorts of different orientations, positions, and so on. Let me see. And this direction is better. And then if any of them is not useful, MATLAB is going to tell me that, hey, you need to recapture. So here you have some settings, as you can see. There is the capture interval, how many seconds, how often do you want the software to take a picture, how many pictures do you want it to take. So let's say, for example, I want, let's say 6 pictures, and every, let's say 3 seconds or every 4 seconds, you capture a picture, and then it is going to save them all under downloads for me also. So once I say capture, see what's going to happen. Here we go. So this is going to be first one. And you clearly see once it takes a picture, it is going to appear on the left-hand side, right? You see some of the images I make deliberately to not have all of the chessboard in them. And we'll see if MATLAB is going to take them from me or is asking for another recapture. Here we go. So far I have 6 images, right? You can see them all on the left side. This one, the 4th one, is definitely not a good one. But you see here, it is still processing. So you have to be patient and allow MATLAB to process and tells you whether any of them should be recaptured. And then, as I said, you need at least 20 pictures. So you need to keep repeating this until you get all of the images that you need. One other thing you need to do is to measure the size of the side of one of these chess cells in millimeters or meters or inches and report it. So this is the part, this is the information that it needs in order to be able to do the calibration. Because remember, based on what we learned in the previous lecture, you need what? You need the coordinates of some real points P in the world coordinate X, Y, and Z, right? You need these guys, X, Y, and Z. And guess what? How do you get all of these points? How do you get all of these X, Y, Z's, right? This is what MATLAB does. So this is the base of the calibration. So it assumes that you laid the paper on a flat piece of surface, and it assumes that the Z for all of those points on the chessboard pattern are 0. So assumes that you are putting it on the XY plane. Can it do it? Yes. The origin of the word frame is completely up to you to decide. So what it did, it chose the top left corner of the chessboard to be the origin, not all of it, the interior of it. We'll talk about it, the interior of it. It chose one point on the chessboard to be what? To be the origin of the word frame, Z-axis to be downward, but as I said, all of the points are on a flat piece of paper, so all of the points have Z of 0, capital Z of 0. What about their X's and Y's? So it assumes that one of the points is at 0 and 0, right? One of the chessboard corners are at 0, 0. How does it find the coordinate of the rest of the points on the chessboard? Based on this dimension that you are going to enter. So here, let's say for this piece of paper I printed, each side of a cell corresponded to 29 mils. Use your ruler and measure that, and then tell it whether your images that you think you got are high distortions or low distortions. Let's say I'm okay. I don't think my images are highly distorted, and 29 mils. And now it is detecting the checkerboard in all of the 6 images. And if for any of them it cannot do a good job, it is going to tell you. Okay, so here it gives you this window and say, hey, I got 6 images and none of them was rejected, but 2 of them I could only partially detect the chessboard. Okay. So it did not really reject any of that. That's a good thing. But if it did, for any reason, if it did, then it would ask you, it would tell you, hey, 3 out of 6 are rejected. So literally only 3 of them worth anything, right? But now, as I told you, it is going to detect the corner points. Let me show you on this picture. So you will see something like this. It is going to detect, as you can see, the inner layer of the chessboard. All of the points that are detected are shown with a green circle. The origin, the point 0 and 0, this point is shown with a yellow square. And it can keep detecting the very same point in all images as long as your chessboard is not symmetric 8 by 8. As you see, I made it 7 by 8. Correct? We'll talk about the red cross points, the reprojected points later. But that's what it is. If this point is 0, 0, and this is the x-axis, and this the upward direction is y, so what's the coordinate of this point here? Right? If I say, let me show you. So this point, the x, y, z for it is 0, 0, 0, right? What is this point? Well, that's along the x-axis, and each side is 29 mils, so that is like 29, 0, and 0, right? This point here, for example, is what? It's 2 unit x, 2 unit y, so it's like 58 x, 50 y, 8 y, and then 0 z. So it can detect the x, y, z coordinate for each and every one of these points, and since they are a corner point, detecting their pixel coordinate in an image is not a hard thing. We'll later have a video on corner detection, right? And I'll show you that the corner detection using computer vision is not the hardest thing in the world. So detecting U and V for these pixels is also not a hard thing, right? So it is going to detect all of these images, and once you have 20 of them at least, then you can go to the calibration and then click here and say calibrate, right? So here, this is what I will do instead. Let me close this, and then instead I relaunch it with my save data. Okay, so here I say from file. I have already chosen all of these images, and here again I provide the size of each side. It is going to detect the checkerboard in these images and tell you if you have 20 good images or not. Then you can proceed. There are some settings that you can do for calibration. You can tell it whether it has a fisheye scaling or not, whether it's a wide lens or not. You can tell it. There are some other things that you can do in the option. I'm going to tell you, but you can see here out of the 46 images, 15 of them were rejected. You can click on the rejected ones. 31 were good. Okay, so all of these 31 images are good, and you can see clearly now when I go from one image to the next, it constantly and consistently detected this bottom right corner as the origin, and it could detect all of the other 6x7 42 corner points. Okay, so it did get more than what it wanted. You see some images like this are not good. This image 30 you see clearly because it's partially visible, right? So if you want, you can right click and remove it. If you see some bad images, go ahead and get rid of them. Okay, it says for a good calibration you need 10 to 20 images. I would say 20. Okay, but any of these images for any reason is partially visible, or you see the corners are badly detected or not detected, get rid of them. So now I have enough images. As I said, you can do some settings here, right? You can go to options, and here it allows you to also calculate the skew, the tangential distortion, and the radial distortion. What are these? So let's talk about it. So what does skew mean? Skew mean the effect of X projection on Y and Y projection on X. What does that mean? It means if we go and look at the K matrix, the intrinsic projection matrix, if you remember from the previous video, the shape of it in general is like what? It's like alpha 0, U naught 0, beta V naught 0, 0, 1, or this element can change a little bit to be negative alpha cotangent of theta. This element can change if theta is not 90 degrees, the angle between U and V axis. But this element here is always 0, right? So now if we go back and look at this case here, this matrix that you see here is the same as that K, except it is the transpose of that. So one thing that you have to recognize when you use the camera calibration app, the K that you see is the transpose of the K that we introduced in the previous video. So if I look, instead of U naught and V naught being element 1, 3, and 2, 3, they are element 3, 1, and 3, 2. Okay, so if I want to say what? K transpose here, right? What's going to be? It is going to be like this, as you can see, right? And so the skew factor, or S, that you can see here, it is coming from what? This one. It is coming from negative alpha cotangent of theta. Well, alpha is a constant number. The only reason that number is not equal to 0 is because cotangent of theta is not equal to 0, and that means theta is not equal to pi over 2. So the skew comes from the fact that U and V axis are not perpendicular to each other, as we mentioned, and that changes your simple K matrix to a little bit more complicated. So this K matrix always has this parameter that we call it the skew parameter. So when you check that, it means I assume that what? When you say check for a skew, means I assume that theta is not equal to pi over 2. Okay, that's the skew. But what is radial and tangential distortions? So for radial distortion, the X that should go and be projected on the physical retina, it's not going to go straight to the place that it's supposed to go. It is going to bend a little bit radially. So let me show you that as well in one of these pictures here. So this light ray that should come through point O and then P hat and P is kind of like general relativity, right? On the way, it could be a little bit distorted and end up on this point P prime instead of P. The difference between P and P prime does depend on where the point P was in terms of its radial location R and its basically theta angle. This theta is different than the theta between U and V axis. So maybe we introduce another angle instead of theta. Instead of theta, maybe I call it gamma or something. So R and gamma are the polar coordinates of the actual projection point. Based on those, your actual projection point will be modified to this distorted projection point. And how are they distorted? For radial projection, these are the governing equations. The X distorted is going to be the X actual plus some extra terms. And Y distorted is going to be Y actual, again, plus some extra terms. Where, what is this R squared? You see here, there is R squared. R squared is what? X squared plus Y squared of that point. As I said, it's radial coordinate, polar coordinate. So R to the 4 is R squared, square of it, and that's R squared to the power 3. Now, you see it said 2 or 3 coefficients. 2 means only what? K1 and K2 are to be calculated. K3, I assume it's 0. When you say 3 coefficients, means this guy is also what? Not equal to 0. So depending on whether you choose radial distortion or not, and how many coefficients you want to calculate, not only it will give you all of those 11 parameters that you had, correct? Remember, you had 11 parameters, intrinsic and extrinsic. So now when you choose radial distortion, it is also going to calculate for you K1 and K2 for 2 coefficients and K3 for 3 coefficients, right? So it is going to estimate 14 parameters for you. Now, what's the effect of these exactly in the image? So there are 2 different versions of it. One is called the positive radial distortion. The other one is negative, or we call them barrel and the pincushion. So in one of them, the points are basically projected in a little bit radially outward direction. So it's like this square that you had is now being radially expanded. That's because these coefficients K1, K2, and K3 are positive. And in the other one, it's like basically that the square is being shrunken. Right? That's because those KI's are negative here, or at least some of them are negative. Here they are positive, and here they are 0. Okay, so depending on the sign and how many of them, you will get different amount of radial distortion. And tangential distortion is quite something similar. The reason for tangential distortion is because not because the lens is imperfect. Radial distortion is because the lens is not perfect. What about tangential distortion? It's because the lens and the physical retina or camera CCD sensor are not parallel. They are at some angle like this. They are not completely parallel like that. That causes some tangential distortion. The equations for tangential distortions are like this. And as you can see, the distortion, the X distorted, is different from X based on not only the radial location of the point, not based on the X and Y of the point, but also there are two coefficients P1 and P2 involved. So if you want tangential distortion to be calculated, in addition to the 11 parameters and 3 Ks, now you will also have P1 and P2. So it needs now at least 16 coefficients to be calculated, and you definitely need more than 16 points, capital P and small p pairs, to be given to it. That's why we say typically 20 points is the minimal thing that you need. Okay, and these distortions make your equations now nonlinear, so calculating these extra coefficients is quite more demanding computationally and mathematically compared to when you just did everything using basic linear algebra as we did in the previous video. Okay, so if you check any of these, especially the radial or tangential, be prepared for a little bit extra time of the software. And now when everything is good, you can go ahead and start the calibration. It does that for you. It shows a camera-centric view or a pattern-centric view. I recommend you use pattern-centric. Why? Because this one is like you put the camera in a fixed position orientation and move the chessboard around the camera. This one is what we did. We put down the chessboard pattern, did not move it, but we did move the camera around and rotate it. So this is the realistic thing of what we did, which you can see in this picture here, right? So it shows you where the camera was and at what orientation it was with respect to the paper in each picture that you took. So basically, what parameters can you see here kind of visually? If I say out of all of those 16 parameters, which one can you see in this picture? These are the rotation matrices and the translation vectors, R and T. Okay, so R and T, the extrinsic parameters, are what you can see in this picture to some extent. Good, so we got that. It also shows you this one here. This guy, it shows you basically the min error in pixels. And what is this one? This one is now the reprojection of the points and the difference between the reprojected points and the actual points, whether they match or not. And what is reprojected points? Well, reprojected point means what? Means, guess what? Now that I calculated all of these parameters, right? Extrinsic, intrinsic, and everything, can I get now my pixel coordinate P small? Yes, if you remember, it was 1 over z m times capital P. And my capital P's are, I told you how to calculate the x, y, z of each one of these points. So I know them. My M matrix is calculated because now I have all the parameters. The Z can be calculated from M and P. Remember, it's M3.P. And so from here, I can calculate what? Recalculate the pixel coordinate for each and every one of these physical 3D points. And then I show them with the red cross. And then I'll see whether the red cross would fall on the top of the green circle and inside it. If it does, that means my parameters that I estimated were really good. But if you see a red cross falls outside the green circle, it means there is a mismatch, there is some pixel error. And if the pixel error is big, it means the distortions were not calculated, the calibration was not done properly, and that's a red flag. Another thing I want you to make sure is this yellow square, the origin, is the same location in each and every one of the images. If from one image to the next, it has moved from one corner to another corner of the chessboard, that's a big red flag. You have to redo your calculations. The biggest reason for it, I told you, is because the chessboard could be asymmetric. But you see here, as you can see, the mean error in pixels is less than 1. And less than 1 pixel in an image is no big deal, because it physically means it has not really moved, right? Because you cannot really see less than a pixel in any image. So as long as this min error pixel is less than 1, you really do not have much of an error and you're good to go. Now you can export your camera parameters, either generate a MATLAB script that basically shows you how to do it using a MATLAB code. So here you see all of the images are read from my download folder, and then they are all read in, correct? And then I run these built-in functions like estimate camera parameters and so on and so forth, right? Display everything. So if you really want to know how MATLAB is doing it, you have to see inside this, like this function. This is the main function here. You can right-click on it and say open it. And this is where the actual computations in MATLAB is shown. You see here, this is where it calculates the M matrix and all of those P and Ks. So you can go down, right, and you can see how it is actually mathematically done. Okay, it has a lot of lines of code, so you have to go through it. Many of that are those math formulas that I showed you last time, these guys. But it has definitely a lot more because it added all of those radial and tangential distortions that we did not. Okay, so you have to go and decipher exactly how each and every one of these is done for you here, right? And you can learn about how the computation is done in MATLAB code. Or if you don't care about how MATLAB did it, all you care about is just those parameters that you want, then you go here and say what? Just export the parameters to the workspace, and it says fine, what do you want me to call them? You say camera params. You can also estimate your errors if you want. If you don't care about them, just say okay. So now you go to your workspace, you see a structure called camera params is exported to the workspace. It is a structure and it has several fields or properties. One of them is, or it's really an object if it has properties. One of them is intrinsics. Then you have extrinsics, right? Rotation matrices, translation vectors, right? All of the calibration setting and so on. So let's say what? You want to see the K matrix, the intrinsic matrix. So what do you say? You say camera params dot, and then what? Camera intrinsics, right? So you say this, and then dot, and then bring the name of the field. 1 second. And you cannot have spaces. You have to say just intrinsics, I assume. Let's see. Here we go. So camera params dot intrinsics. This is those intrinsics. It shows you those focal length values. What are these? These are the alphas and beta. This is alpha and beta. Or a lambda, which is focal length times sx and sy. Right? So this is alpha, this is beta. This is U naught, this is V naught. And then these are the coefficients for radial distortions, K1 and K2. You only chose 2 coefficients, so there is no K3. You did not choose a skew, so theta is 0. The theta is pi over 2, or there is no skew, or cotangent of theta is 0. The tangential distortion, P1 and P2 are both 0 because you did not want them. And if you want, you can get the whole K matrix here as an intrinsic matrix. So here, I say dot and then say intrinsic matrix, and this is your K matrix. Good. Now, if you also want what? You want to see the translation or the rotation matrix for each and every one of those positions, then all you need is to pass it through the camera params, and here you see This is the rotation matrix for the first picture. This is the rotation matrix for the second picture, and so on, all the way to what? To the 30th picture. And then you can also look at the translation vectors. Right? So if you do that, it should also show you all of those translation vectors. Each row corresponds to one of the images. So here we go. This is how you get all of the camera parameters. Note that for the entire set of images, there is only one K matrix, right? Because that's inside the camera. Inside the camera, you could not change. But for each image, you have one set of R and T. Why? Because each image is taken at a different position and orientation. So hopefully this was useful to you, how to do the calibration, what's the meaning of calibration, how to see the code of it and everything in MATLAB. And I will see you in my next video. Thank you.